Hi, welcome back. So in this video, we're going through two examples of finding eigenvalues. We've gone through the process now of how we find eigenvalues, and we're just going to put this in practice through two examples. So let's find the characteristic polynomial and the eigenvalues for the following matrices. We'll take A, a 2 by 2 matrix, where the first row is 9, 6, and the second row is -10, -7. And we'll take B, a 3 by 3 matrix, where the first row is -2, 0, 0, the second row is 0, -2, 0, and the third row is 4, 8, 4. So this is like two separate problems we're going to do. We'll find the characteristic polynomial and eigenvalues for each of these matrices. I'll do the calculations for matrix A by hand, and we'll use some technology to help us out with the matrix B, although we'll actually do most of it by hand for that one too. So I want to let you try these ones on your own, but before I send you to do that, let's remind ourselves of the steps that we follow. So our first step is to write A minus lambda I, or it'll be B minus lambda I for the B matrix. Then we compute the determinant of this matrix, which gives us the characteristic polynomial. So we're looking for the characteristic polynomial as a part of this question, and then we're going to use that characteristic polynomial to find the eigenvalues. So in the third step, we'll find the eigenvalues by taking the determinant of A minus lambda I and setting it equal to 0 to solve for lambda. This is finding the roots of the characteristic polynomial that we found in step 2. So why don't you go ahead, pause the video now, and try this out on your own. We're finding the characteristic polynomial and the eigenvalues for both of these matrices. Alright, so let's start with matrix A. Our first step is to write the matrix A minus lambda I. So I take A, 9, 6, -10, -7, and I subtract lambda times the identity, 1, 0, 0, 1. So I just need to simplify. I distribute lambda into that identity, so I have lambdas on the diagonal, and then I combine the matrices. So I'm getting 9 minus lambda, 6 minus 0, -10 minus 0, and then -7 minus lambda. Then those minus zeros aren't affecting anything, so I'll just take those away, and I'm left here with my matrix A minus lambda I. You can just think of taking those elements on the diagonal of A and subtracting lambda from them. Alright, now we're going to take the determinant of this new matrix we found. So I'm taking the determinant of A minus lambda I. I'll use the vertical bars to represent the determinant. And remember, the determinant of a 2 by 2 matrix is AD minus BC. So we kind of do one diagonal minus the other diagonal. So I'm getting 9 minus lambda times -7 minus lambda, and then I'll subtract 6 times -10. Alright, so we're getting our characteristic polynomial here. This just looks a little messy as it's written, and we're going to need to set this equal to 0 in the next step, so I'll go ahead and simplify it now. Let's distribute everything and combine like terms. So first I'm doing 9 times -7 is -63. Then I have minus 9 lambda plus 7 lambda, and then plus lambda squared. Then I have a plus 60 at the end. So combining like terms, I'm getting lambda squared minus 2 lambda minus 3. And this is my characteristic polynomial for the matrix A. Now we're just left to find the eigenvalues, so I'm going to take this characteristic polynomial and set it equal to 0, because I'm taking the determinant of A minus lambda I and setting it equal to 0. So I'm seeing here that I can factor this into lambda minus 3 and lambda plus 1. That gives me the -3 for the multiplication and the minus 2 for the addition. So to finish off, I'll just set each of these terms equal to 0 and solve, which results in lambda equals 3 and lambda equals -1. And these are my two eigenvalues for the matrix A. Alright, there we go. Let's do this again with matrix B. So I've written here that we're finding A minus lambda I, but it's really B minus lambda I. So I'm writing my B matrix here, and then I subtract lambda times the identity. That lambda gets distributed into the identity, so it's just lambdas on the diagonal. And then I combine the matrices. So in the first row, I have -2 minus lambda, 0, 0. The second row, I have 0, -2 minus lambda, 0. And the third row, I have 4, 8, 4 minus lambda. So I've just taken the diagonal of B, and I've subtracted lambda from each of those terms. And this is the matrix we're going to be using. Now, for the second step, I need to take the determinant of this matrix. Again, I'm writing A minus lambda I here, but we're really doing B minus lambda I. So I'm taking the determinant of this matrix. When I do this, I'm going to expand along the first row. So I'm going to take -2 minus lambda and multiply it by the determinant of the remaining parts when I cross out that row in the column. So I'm taking the determinant of -2 minus lambda, 0, and then 8, 4 minus lambda. Then going across that first row, I would subtract 0 times the determinant of what's left, but 0 times anything is 0. And then I would add 0 for that third term times the determinant of what's left, but again, the 0 means that it's going to go away. So I really just have 2 minus lambda times this determinant. So okay, let's do this. For the determinant, we do -2 minus lambda times 4 minus lambda, and then we subtract 0 times 8. So what I'm getting is -2 minus lambda times -2 minus lambda times 4 minus lambda. And this is my characteristic polynomial. Alright, so before we go on to the third step where we find the roots of this polynomial, I just want to show you a way that you can use technology to help you out with this process if it's more complicated. So you can ask Wolfram Alpha a lot of things about a matrix. You can actually just give it the matrix and it should tell you information like the characteristic polynomial and the eigenvalues. But I'll show you here that we can simply just type in the specific operation we want. So I'm computing the determinant of this matrix here. So I've typed in the rows where I have my -2 minus lambda, -2 minus lambda, and 4 minus lambda. And we see here that we get the result, which is the determinant, is negative lambda cubed plus 12 lambda plus 16. And so this is also my characteristic polynomial. This is just a rewritten version of what we already found. So we found a factored version that came from the determinant, but if we were to multiply all of that out, we would get this as our polynomial. I just want to show you this because sometimes you might compute a determinant and it might be kind of complicated looking, and so using Wolfram Alpha to find it for you can be really helpful. Moreover, if I was given this polynomial, negative lambda cubed plus 12 lambda plus 16, it might take me a while to figure out how to factor it. So having technology to help us do that step could be nice too. You could ask it to factor this polynomial or just set this polynomial equal to 0 and it will tell you the roots. But since we already have the factored version, we can do this by hand. So I'm setting my determinant equal to 0. So I have -2 minus lambda times -2 minus lambda times 4 minus lambda, and I'm setting this equal to 0. To solve, I'll just set each of the terms equal to 0. So I'm getting -2 minus lambda equals 0. I'm getting that again for the second term, and then I'm getting 4 minus lambda equals to 0 for the third term. This results in my eigenvalues -2 equals lambda, -2 equals lambda, and 4 equals lambda. So we're in an interesting case here where we have a repeated eigenvalue. So one of the ways I might say this is that we have two eigenvalues. Our eigenvalues are -2 and 4, and in this case the eigenvalues have different multiplicities. So we would say that the eigenvalue -2 has multiplicity 2, and the eigenvalue 4 has multiplicity 1. So this is one of the ways we can just say a little bit more about the eigenvalues and how they're showing up. So you'll see here I can actually use Wolfram Alpha to help us out with this. So I can just ask for the eigenvalues of the matrix B that we started with, and it's going to give me these three results. It gives me that my first eigenvalue is 4, and then my next two eigenvalues are both -2. So when we see that 4 appearing once, that has multiplicity 1, and when we see that -2 appearing twice, this would have multiplicity 2. And there you go. So for this 3x3 matrix, we were able to compute the eigenvalues by hand, but oftentimes when we get into these higher dimensional matrices, it's nice to have technology on our side to help us out to do the computations. That's it for this one. Thanks so much for watching, and I will talk to you in the next one.